In this lesson, we're going to have a look at balancing equations. So first, it's important to review the law of conservation of mass, which states that the mass during a chemical reaction remains unchanged. Because we can't create or destroy atoms during the process of a chemical reaction, and the atoms are really simply rearranged to make new substances, this law is followed in all cases. The first thing that we want to do is look at a chemical reaction that has been unbalanced which is called a skeleton equation. So let's look at this example here. We've got CH4 plus O2 going to CO2 plus H2O. And this is a combustion reaction. When we look at the visual that we have here, where we are counting the atoms that we have in our reactants and products, when we look at CH4 plus O2, we can see that we have a total of 1 carbon atom, 4 hydrogen atoms, and 2 oxygen atoms in the reactant side. When we look at the products, we have 1 carbon, we have 2 hydrogens, and we have a total of 3 oxygens. So there's 2 oxygens in the CO2 and there's 1 oxygen in the water for a total of 3. You can see in this visual as well, the numbers that I've written down here match the visual. Now, this skeleton equation is not balanced. We have the correct number of carbons on both sides, but we don't have the correct number of hydrogens or oxygens. They need to be the same on both sides. That's how we'll know that the law of conservation of mass has been observed. So I've already balanced this equation. Okay, we're not starting with balancing, we're starting with just examining for a moment. When we look at the equation that's balanced, what you can see is that what I've changed is I've put numbers out in front here. So I haven't changed the formulas that I have. I still have CH4 plus O2 producing CO2 plus H2O. However, what's changed is I've added these coefficients. And that's really telling me how many of that thing I want in my chemical reaction. If you think of a chemical reaction like a recipe, it's telling me you need 2 oxygens for every 1 CH4. So if you compare the before and after here, I only had 1 oxygen before, which gave me 2 oxygen atoms. And now by having 2 O2s, that will give me a total of 4 oxygens on my reactant side. And then as well, I've got 1 carbon still and 4 hydrogens. Okay, you can see in a couple of different ways. And then in the product side, I've got 1 carbon. I've got 4 hydrogens because I have 2 water molecules. Okay, and so each water molecule, if I look at 1 water molecule, that has 2 hydrogens and 1 oxygen. So if I have 2 water molecules, okay, which I can look at visually as 2 individual water molecules, or think of as 2 H2O or 2 water molecules, then when I look at the total that I have, this gives me a total of 4 hydrogens and 2 oxygens. Okay, so because I have 2 H2O, that gives me my 4 hydrogens. Now for the oxygen, I just want to be careful because it's in both molecules. So I see over here, I've already tallied that in my 2 waters, I'm going to have 2 oxygens. And then in my 1 CO2, I'm going to have an additional 2 oxygens. And that gives me a total of 4 oxygens. So you can see in the before and after that what has happened is by adding the coefficients, the proper coefficients in front of the elements and compounds in my equation, I'm able to correct my skeleton equation and make it balanced so that the atoms on the left, or in the reactants, are equal to the atoms in the products. Now, how do we do that? So how do we go from a skeleton equation to a balanced chemical equation? So again, we're connecting here to the law of conservation of mass by saying that the mass will be equal on both sides. So in this skeleton equation, I have aluminum reacting with chlorine to produce aluminum chloride. And when I just move left to right and I count up my atoms, on the left-hand side in the reactants, I have 1 aluminum atom and I have 2 chlorine atoms. Whereas on the right-hand side, I have 1 aluminum atom and 3 chlorine atoms. So my skeleton equation is not balanced. Now what we need to do here is we need to think about, what is our common multiple? Like, what can we do to make these two equal to each other? I need to change the coefficient, or the number in front of the formula, so that I can make it so that the atoms are the same on both sides. So a common multiple between 2 and 3 is 6. So I can say to myself, okay, if I want 6 chlorines on this side, what number should I put in front so that I have a total of 6 chlorines? And so if I choose to take 3 chlorines, we can see what that actually is I have Cl2, Cl2, Cl2. So this is a total of 6 chlorine atoms. I can also think about it as multiplying it out. 3 times 2 is 6. So I've made the atoms on the left 6 for the chlorine, and I need to do the same for the chlorine on the right-hand side. On the right-hand side, I have a 3 in the formula, so I need to put the coefficient of 2 so that 2 times 3 is equal to 6, right? So if I have AlCl3, if I have 1 of those, there's only 3 chlorines, but if I have 2 of those, there are 6 chlorines. Now by doing that, I've balanced the chlorine atoms, but I can see my previously balanced aluminum are no longer balanced, because at this point now I have 2 aluminums on the right-hand side and only 1 aluminum on the left-hand side. So what do I need to do? I need to add a coefficient of 2 in front of the aluminum in order to make it so that both the aluminum and the chlorine are balanced. So essentially, what do you need to do? You need to, in this trial and error process, balance the atoms systematically, one by one, and check your work until you have the equation balanced. So we do have a general order for balancing equations, and we will look at this order and then we'll do some practice. So essentially, you're going to focus on balancing everything except for oxygen and hydrogen. And I'm going to invite you to think about polyatomic ions as a group of atoms. We'll see some examples in a moment. Then you're going to balance hydrogen, then oxygen. So essentially, as a general rule, you leave oxygen till the end, balance hydrogen second last, okay, and everything else before that. Now, there's a few things that you need to do at the end. You need to just double check, like we did here, where we check all of the atoms on the left and the right. And then you also need to make sure that the coefficients are in the lowest possible ratio. Okay, so let's look at a couple of examples here. Now, my general strategy is to move left to right following that order. So we've got basically oxygen. We've got oxygen last, we've got hydrogen second last, and we've got the other beforehand. Okay, so if I examine this first one, I've got K, so I've got 1 potassium on the left-hand side. So I look on the right-hand side, I also have 1 potassium. Okay, So I didn't make it totally clear before. I made an assumption here. There is a 1 assumed to start with, right? So you have, right now, the reaction is saying that you need 1 potassium and 1 chlorine to make 1 KCl, or potassium chloride. So my potassium is balanced at the moment. So then I have a look at the chlorine. There are 2 chlorines on the left and only 1 on the right-hand side. So I'm going to put a coefficient of 2. And then I need to check again, because as soon as I make 1 change, I need to make sure that it's still balanced for the other elements. Now I have 2 potassiums on the right-hand side, So then I need to put a 2 in front of here so that the entire equation is balanced. In B here, I'm showing you an example where you've got a polyatomic ion. So a polyatomic ion is a group of atoms that overall has a charge. So these hydroxides, these nitrates, these are polyatomic ions. And at this stage, you just want to recognize them as this group that stays all together. And so you can count it as one entire piece. So let's move through going left to right, looking at atoms and polyatomic ions. Okay, so iron, I've got 1 iron on the left and I've got 1 iron on the right. Okay, so that's balanced so far. This group of atoms here, this nitrate, which you can see it helps to look at it in brackets, I've got 3 of them. So I've got NO3 3 times. On the right-hand side, I've got NO3, but there's no number there, so I've basically got it 1 time. So to balance that, I need to put a 3 out front. So notice that the only thing I can do to make it balance is by adding coefficients. I cannot change the formulas of the reactants and the products. I can only change the ratio that they're reacting. Moving on, continuing through, so Cu, there is 1 on this side, but now that I've got a 3 out front, I've got 3 coppers on the right-hand side. So I need to put a 3 out in front of the copper 1 hydroxide. And lastly, with the OH, which I see on this side in brackets, I've got 3 on the right-hand side, and I've also got 3 now on the left-hand side, because I have 3 copper hydroxide. Using the gizmos can help you to check your work, okay? And you can also write things out if you need to. So when I look at 3 times CuOH, what does that mean? It means I have 1, 2, 3 copper hydroxide in my recipe. So what does that mean? I have 1, 2, 3 copper, and I have 1, 2, 3 hydroxide. Okay? So part of the key here is being confident in your counting of the atoms and of the polyatomic ions. Okay, so I can do a quick scan again, and I'll see that this is in fact balanced. Okay, I would clean it up so that I just have the coefficients. And what this is now telling me is that for this reaction, I need 1 iron 3 nitrate to react with 3 copper 1 hydroxide to produce my products. In this last example here, we're looking at a combustion reaction where we have C7H16, and it's reacting with oxygen to produce our CO2 and H2O. And combustion reactions are particularly tricky sometimes, and so it's really useful to follow the order that I've previously suggested. So we're going to do oxygen last, and we're going to do hydrogen second last. And the reason for that is because oxygen is part of 2 separate compounds on the right-hand side. So moving left to right, and carbon being first, I've got 7 carbons on the left, so I need 7 in front of the CO2. Then I've got 16 hydrogens. So how many H2O do I need? I need 8 waters so that I can have 8 times 2 or 16 hydrogens. Now tallying up the oxygens on the right-hand side, I've got 14 I've got 7 CO2 plus 8, which gives me a total of 22. I've got 22 oxygens on the right-hand side. So my last step is to balance the oxygens. And I'm going to put the appropriate coefficient, which is going to be 11 oxygen, so that I can have 11 times 2 is 22. In this last question, we're looking at a skeleton equation and then a supposed balanced equation. Okay, so if we look at this, the atoms on the right and the left are the same. But what has gone wrong with this balancing is that they've changed the formulas. So we don't balance by changing the formulas, we balance by adding coefficients in front of the formulas, by changing the ratio in which they will react. So for this one, N2, I need 2 NH3. And then when I now check this, I've got 6 hydrogens on the right-hand side. So I need 6 hydrogens on the left-hand side. And so the difference is I don't have 1 nitrogen and 1 H3. H3 doesn't exist. I have 1 nitrogen reacts with 3 hydrogen to give me 2 NH3 molecules. The biggest piece of advice I can give you about balancing is to be patient. It's a trial and error process for a reason, because as you change one number, sometimes another number gets changed. Move slowly, check your work at the end, and have some fun.